Okay, here we go again. So, hopefully the first lecture was primarily review. The second lecture is something that maybe you haven't seen before in as much detail. This is going to be about open quantum systems. So basically the second lecture is basically, everybody knows the quantum mechanics is governed by evolution, that's given by the Schrödinger equation or the Heisenberg equation of motion, if you prefer to work in that picture, right? But that's only one possible way in which a system can evolve, and this is going to be dealing with evolution that's not given by that kind of Hamiltonian generated dynamics. And so we're going to look at how we can just take the laws of quantum mechanics, make some assumptions about interactions with an open system, and then derive new, seemingly different phenomena from that kind of picture. So there'll be a lot more pictures in this talk, though the math, when it does appear, is a little bit intimidating. So the idea of a reservoir it's a large system which is coupled relatively weakly with a much smaller system. And there's three important axioms that we use when deriving these results for open quantum systems. So first of all, the reservoir is so large that any energy or any interaction, anything that's transferred between our little subsystem and the reservoir is not changed. The reservoir state is basically time independent. The reservoir has a broadband spectrum, and what I mean by that is that it is a system which is comprised of many, say, oscillators that are going at different frequencies. So you could think of, say, if I have a spring, like in the simple example, spring hooked up to the ceiling can be vibrating at many different frequencies due to the phonons, the different phonons of frequencies in the ceiling, like way back in that first picture of the quantum harmonic oscillator. So it has oscillators going at very many different frequencies. And the reservoir is also, it's in thermodynamic equilibrium. And so what that means in quantum mechanics is that the density matrix is given by this thermally equilibrated density matrix, which is e to the minus beta h, basically. Now, this basically, the reason why this gives you thermal equilibrium is that this maximizes the entropy for a given fixed energy. And so that's what we mean by thermodynamic equilibrium, both in classical and quantum systems. Remember, beta is just 1 over kT. All right, so you can do a lot of interesting physics relaxing one or two of these assumptions about the reservoir, but that's really complicated. So we'll just kind of stick with this traditional picture of an open quantum system, which has these three nice properties. All right, so we assume basically that initially we're going to hook the quantum system up to this reservoir. The two states, the state of the reservoir isn't entangled with the state of the system at all in the interaction. I can just switch the interaction on at time t equals 0. And so that means that the density matrix, the combined density matrix for the system and the reservoir, will factorize in this nice way. So the system is in whatever state it is in, the reservoir is in its thermal equilibrium, and they're just uncorrelated. They're just a direct product. Now, there's a Hamiltonian, there's going to be, the evolution will follow, the combined system and reservoir will follow the traditional Schrödinger evolution given by some Hamiltonian which incorporates both the system, the reservoir, and their interactions. So there'll be some global Hamiltonian that gives our evolution. But the thing is, we don't really measure the reservoir. We're not looking at reservoir observables. We're only looking at the system, the subsystems observables. And so when we do a trace, right, when we look at the expectation value of an operator, we do a trace over both the system and the reservoir. but that can be broken down. A trace over two systems is equal to the trace over one and then the trace over the other. And so if I do those sequentially, the trace over the reservoir, the observable A, the system observable, get the lights again. So system observable A, and now I'm going to, now that I've got the lights, I'm going to write. Basically, the observable A can be written like this. As a product of some system variable with the identity. It's the identity on the reservoir. That's what we mean when we say, okay, we're only looking at system observables. And so that means I can move one of these traces, these partial traces, in.
I'm trying to get the light just on that side.
Oh.
I'm not sure what to do. We need an experiment.
Nope. Oh, I'll let Pierre keep doing that while I. Sure. All right. So our goal is basically to derive what we call a master equation, and that's going to. We only really want to look at evolution of the system piece of the density matrix. We want to just trace out the reservoir variables and look at the evolution of this reduced system, even though there's an interaction that still goes between the system and the reservoir. And so we're looking for some way to approximate that based on those axioms of the open system that we talked about previously. So to derive it, it helps to have a concrete picture in mind, and so we'll look at the simple case of a single harmonic oscillator, our system, interacting with a reservoir comprised of a bunch of harmonic oscillators. So this can be, for example, the free space electromagnetic field. This has a bunch of modes, a continuum of modes in a free space, or a series of discrete modes in a cavity. Or if we talk about a mechanical oscillator, it can be, as I mentioned, it can be hooked up. So some small harmonic oscillator hooked up to a very large, anchored to a very large system which has its own vibrations going on. And there's many other examples. So, as I mentioned, the Hamiltonian for this combined system breaks down into just a pure free evolution for the system, the free evolution for the reservoir, which is thermally equilibrated, and then there's an interaction between the system and the reservoir. And so, for a harmonic oscillator, our system is just a system Hamiltonian is just a single oscillator frequency omega. A reservoir Hamiltonian is a sum over a bunch of independent modes at different frequencies omega j. So this is the broadband assumption, is that these omega j's will vary from very large to very small relative to this system frequency capital omega. And the interaction Hamiltonian, and so what this does, this is a form that kind of makes sense. It's got these two terms here, which basically just take, in one case they take and they destroy a phonon in the reservoir and add a phonon to the oscillator, our subsystem. And in the other case, you destroy a phonon in our harmonic oscillator subsystem and transfer one, you create one in the reservoir at some particular frequency. And of course, the probability for this to happen will be largest at the frequencies which are closely matched with the system frequency, as we'll see later. And so this is kind of a very simple generic interaction Hamiltonian that we might see between our system and reservoir. Okay. So we're going to assume that this interaction is relatively small, so we can do perturbation theory, and we're going to work it out to second order. Now, there's going to be a lot of math here. I think it's probably better just to follow along and maybe, I guess we can just jot down. You can jot down this. So you notice that this interaction factorizes. I can pull out, I can break this into two terms. And I can pull out the A dagger from the first term and the A from the second term. And so, so what I get is this, this reservoir displacement operator, which is a sum over all modes. And so F is the one that annihilates a phonon at each different frequency with a different strength. And I'm looking at this in the interaction picture, so I put in the free evolution of the system and the reservoir, so that means that A dagger picks up a positive e to the I capital omega t, and then the B picks up an e to the minus I omega jt. And so that's what in the interaction picture is time-dependent phase. And so this is what we call the quantum noise operator for the reservoir, and you'll see why later. So it's a sum over all these modes, basically. Now, what we're going to, that should be an approximately equal to sign. What we're going to look at is the a time evolution where when I take a derivative, you know, it's supposed to be d rho dt, but we're really thinking of time dt, which isn't truly infinitesimal, but it's rather, it's actually large. The system evolution happens on a slower, much slower time scale than the reservoir equilibration time scale. And that goes back to the assumption that our reservoir, number one, isn't affected by its interaction with our system, and number two, the reservoir is in thermal equilibrium. So if a phonon gets kicked out of the reservoir and into our oscillator, which is what this first term in the interaction Hamiltonian does, we're going to assume that the reservoir will, from its own environment, reabsorb that energy in a very fast time compared to the evolution of our little small subsystem, the harmonic oscillator. All right, so here's the big, ugly math equation. We can plug in this stuff and go and derive the second order in perturbation theory, the time evolution for the density matrix. And so you see we have two integrals and that's why it's second order perturbation theory. And we get these products of the noise operator at different times. And remember, we're looking at the system evolution. So I'm tracing over the reservoir here for all these reservoir noise operators. Right? So I'm doing the trace over the reservoir. And then this is the reduced density matrix for just the system without the reservoir included. Right? So now if I look at what kind of products that these entail, these F daggers of T double prime F of T and so on and so forth, since this F is just a sum, F is a sum over annihilation operators, F dagger is a sum over creation operators. So what these look like is I have double, and you'll see this on the next slide, I have double sums over I and J of the reservoir expectations, some constants out here. Not important, but these are going to be summed over the expectation values of, say, Bi, Bj, and then if it's, let's say this will be F of T, F of T prime will look like this. Right? So these are summed expectation values in that form. Or if I put a dagger on one of them, then I get a dagger here. Well, in thermal equilibrium, the reservoir is a bunch of harmonic oscillators at different frequencies. When that reaches thermal equilibrium, that's the same as a bunch of independent harmonic oscillators that are all in equilibrium following Bose-Einstein statistics. Right? So those are all independent of each other. And what that means is that if I look at these cross correlations for I not equal to j, that just gives me 0. So those terms are 0 if I doesn't equal j when I'm doing these sums. And if I look at the one without the dagger, if I look at something just like bi squared, that's also equal to 0 for a system in thermal equilibrium. The reason this is kind of like looking at the position of an oscillator in thermal equilibrium while it's at its equilibrium position. And so this gives you 0. The I squared position. But the only terms that will contribute are the ones where it's of the form either BI dagger BI or BI dagger. And as you can imagine, this is given by thermal occupancy of that particular node. All right, well, let's proceed. So based on the fact that if the trace over the reservoir is taken over 2 creation or 2 annihilation operators, I get 0. So these terms immediately cancel out because of the thermal equilibrium assumption. So we've already cut this nasty equation in half. And now we can look at, well, what do these integrals give? Can we make some kind of approximation? And the answer is yes, fortunately. So here's these sums I was talking about. And so they have some numerical coefficients related to the coupling constants. And then we have these, remember these are due to the fact that we're in the interaction picture. These are just the frequencies, the free evolution of the system and the reservoir respectively. Now, as I mentioned, if I look at different modes, I not equal to J, there's no correlation between those when they're in thermal equilibrium, and so those terms give 0, and so I end up only summing, I have a single sum, this thing reduces down to a much more manageable looking single sum over these modes, over one set of modes and one set of reservoir averages.
Sorry?
Yes?
The new value of E and G, is it because you're in thermal equilibrium or because the reservoir is squeezed?
The G or B?
Both. Because if the reservoir is squeezed, the value is not new.
Oh, why is it 0? Was this expectation value 0?
Yeah, the point is that if it's squeezed, it's not in thermal equilibrium.
Oh, yeah, right. Sorry. Of course, yes. If it is squeezed, you're absolutely right. Those aren't 0.
Right.
That would be relaxing some of those assumptions and making things complicated. That's an interesting reservoir, and in fact, my collaborator June has a paper about using a squeezed light to drive a system, and so that's an example where we're not kind of in this thermal equilibrium case. So let's see. So we do this. We want to do this double integral over time, and essentially what we get is this sort of term, which is, technically I have to integrate from negative to infinity, but I'm integrating from a one time to another small, slightly different time. So that's basically 0 to t prime, where t prime is small. It's basically negative infinity to infinity. So this is approximately a delta function. Justifying that is a little complicated, but once I do that, this approximately becomes a delta function. And I also make the replacement that I say, okay, I've got a broadband spectrum. Let's just kind of take the continuum limit of the spectrum, and this becomes now an integral over frequency of g of omega squared times density of states, d of omega, d omega. So once I have that integral over that, with that delta function that kind of pops out approximately from this integral, I only get a contribution from the occupancy right at the system frequency. Okay? So, in other words, what I'm saying is basically, say for conservation of energy, if I scatter a phonon from the reservoir into my oscillator, if it's at a different frequency, I have to take multiple phonons to conserve energy. Right? To excite one phonon in the system, I need maybe a combination of different frequencies of phonons from the reservoir to conserve energy. Right? Well, to lowest order, we just say, okay, the only ones that are going to scatter in from the reservoir are the ones that are right at the mechanical resonance frequency. And so that's a decent approximation. And so again, by making this first approximation that this integral gives me a delta function, and then I take the continuum limit and replace this by an integral over frequency, what I end up picking out is this single mode of the reservoir right at the mechanical resonance frequency. And so this coupling constant, this decay, this ends up being the dissipation constant for my system, and that's related to the density of states in the reservoir at that frequency. So that's the number of channels. You can think of it as that's the number of channels into which a phonon from my system can scatter to the reservoir. And then this coupling strength, right? The stronger the coupling between the system and the reservoir, the faster this dissipative process will happen. So finally, we substitute this all back into we substitute all this back into this equation here, and it simplifies dramatically down to this master equation, where we make the assumption, again, that the reservoir is in thermal equilibrium, so we have Bose-Einstein occupancy, because the reservoir is a bunch of harmonic oscillators. And so we have basically these two processes. Now yeah, this is boring, so a bunch of math, you should be falling asleep. This is a really easy way to interpret this. If I act on the density matrix of the system, remember now, this is an equation of motion just for my system. I've eliminated the reservoir from consideration. The only effects of the reservoir up here determine this constant gamma and then the thermal occupancy n bar. All right? And so what happens, what this term here does is it takes and it annihilates a phonon from the system. Right? And A dagger, remember, if I put it on the right of the density matrix, is acting to the left. Both of those are annihilation operators. A acting to the right, A dagger acting to the left, both annihilation operators. So I'm removing a phonon from my system. Right? And this, if you think of it, this is, it has a kind of a probability which is proportional to n plus 1. On the other hand, what I can do here is I can add. So A dagger acting to the right, A acting to the left. They're both creation operators when I act in those directions. And so that adds a phonon from the reservoir to the system. Now these other terms aren't immediately apparent. They're necessary to preserve the trace of them. They basically appear because you're trying to preserve the trace. Rho has a trace of 1. If I just had this term and this term, that would preserve trace. Okay? And then of course to preserve hermeticity, I also have to add the adjoint. So that's basically what the master equation gives you. So, we can now use this master equation for the system to compute any observable for the system. Right? And so I can look at, for example, the number of phonons. And I can look at an equation of motion for the number of phonons, and I'm going to write on the blackboard again, the whiteboard again. This simplifies down, actually. If I look at, if I just say, okay, I pressed, oh, good, all right. So if I say, okay, I'm going to call n of t, it's just the expectation value of right? So I have dn dt is equal to gamma times n bar minus n. Right? that's no additional manipulation necessary. That's just simplifying this down a little bit. And that equation, you can see if basically if n is greater than n bar, in other words, if I'm exceeding the thermal occupancy, the number of photons is decreasing with time. And if I am less than the thermal occupancy, if n is small, then I increase the number of photons in the system until I reach that thermal occupancy. Now, on the other hand, if I have a displacement, if I look at the expectation value of the operator A, and remember, A is a combination of X and P, right? A is basically, I'm not going to write down the dimension, well, actually I can. So if I write down A is a combination that looks something like this. A equals X 0 point times X hat plus I P 0 point P, right? I put the hats on to clarify which ones are operators and which ones are not. Then what that gives me is two equations of motion for X and P as functions of time. And they both decay. So this, at first glance, looks a little weird. But what I get is what you might expect, right? We're used to seeing a force. We're used to seeing a force that's proportional to velocity, right? A damping force. That's exactly what this term is, and that's something that you see classically. What you're not so used to seeing is this kind of damping where you get directly a kind of a velocity damping. You get position damped directly, right? We're kind of used to seeing momentum as the thing that's being damped. And the reason that this is different is that when we usually see damping, it's viscous damping, right? And that's related to a motion through a fluid. So instead, what we're looking at is a process by which the damping occurs due directly to phonon exchange. So phonons are exchanged from the reservoir of the system, and that allows us, this is a different mechanism for damping than the typical kind of fluid viscous damping. And so this kind of term which we wouldn't expect to see classically, right? So that, I found that a little bit confusing when I first saw this kind of open system stuff. And the reason that's kind of talking about it. Why it's different than what you see in the classical picture for damping is because it's phonon exchange is the mechanism for damping. It's not just an object bouncing around through some fluid which is at rest. So there's slightly different mechanisms. Okay, and the last thing which I leave as an exercise for the interested audience member is to plug in actually the density matrix, the thermally equilibrium, well, not so fast. Plug in this density matrix, e to the, well, you don't need to use the trace. So let's just plug this guy in. Sorry, there we go. Plug that guy in. That's the thermal equilibrium. I can divide by the trace of this if I want to make it normalized. You can plug that into the master equation. Be sure to add the adjoint on. And you can verify, in fact, that this is the steady state solution to the system's density matrix. So in other words, this master equation does indeed produce, as a steady state, a thermally equilibrated system. It has the expected kind of behavior for phonon occupancy. I'm not a morning person, apparently. And it has this kind of expected behavior for the damping with this added twist that the position can be damped directly. It's not just momentum damping as we see with viscous damping for traditional harmonic. All right. Now, that was a density matrix equation. What if I prefer to work in the Heisenberg picture with operators? Well, I can go back to that original system reservoir Hamiltonian, and I can work out the Heisenberg equations of motion for the operators A and all the operators B. So you get just the free evolution of A, the free evolution of each of the B's, and then we get this coupling terms due to the interaction. Now, in principle, of course, these are linear, and so I could I could solve these equations directly with the small problem that I'm dealing with in infinite dimensional matrix, which complicates things somewhat, unfortunately. And so we'll make some approximations similar to the ones we did before. Now, again, remember this operator was what we were calling F before, and so we can just formally integrate. Why don't we go ahead and formally integrate these two equations of motion. First, by integrating the B, I get a free evolution of this kind of term that's been radiated into the system. Right? This is the phonons that are going to be transferred into my system from, these are the phonons that are transferred from my system into the reservoir. That's what's being radiated out. Now I can plug this, once I've integrated this formula, I can plug this back into my equation of motion for A. This equation here, if you're actually copying all this stuff down, this should have an integral in it as well, still. But otherwise it's correct. Now this, if I look at this, well, this is just some initial thing that's evolving, right? I've got just a time evolution multiplied by some initial operator. And then I've got this term, which is proportional to A, T prime. Remember again that it's supposed to be integrated. Right. So because this is A dot is proportional to negative A in some way, that's a damping term. What this is a quantum noise term, and that's again related to that operator F that we saw before. All right, so we go into we do what's called a rotating frame. We just introduce a new operator where we're taking away the free evolution by writing it explicitly here. This will cancel out the e to the minus I omega t that we see in A from this term. When I write down the equation for capital A dot, indeed this free evolution term goes away. And now I'm again going to do a bunch of mathematical tricks to turn these into delta functions and such. So first of all, again, you remember seeing this guy before. That's just the noise operator f of t. When I do all these tricks again, turning this into a continuum integral that turns, pulling this out because it slowly varies, this becomes a delta function. I get another delta function. I get a of t here. It's messy, and we're almost done. Right? So, but what this basically pops out is that gamma, and remember that this little gamma is the same as was defined before. It's basically like 2 pi times the density of states times the coupling at the mechanical frequency squared. Okay, it's the same gamma that we saw in the master equation. Right? Because this is basically the same, very much the similar expression that we were evaluating in that equation. Right? We use the same tricks to make it work out. All right. Well, now we've gone through all that math, and we get what actually looks like a very simple equation for the operator A. It's damped, and it's got a quantum noise piece. Right? And again, we saw this correlation before. We did this computation before, and so in the continuum limit, we can kind of manipulate this, and if we say, okay, I get this weird integral, right? But if I say these variables are slowly varying with omega, I can pull them out of the integral and I get a delta function instead, and so that lets us define gamma as before. And we get these, basically we get these two time correlation for the noise operator. And this is called the Markov approximation. If you are familiar with dynamics at all, Markovian systems are ones with no memory about the past. So this is exactly what we see here. These give you delta correlations in time between these noise operators. So that if the system, if the reservoir kicks the system one instant, the system no longer, the reservoir recuperates immediately and has energy to kick the system again in the next instant with no memory that it just did it previously. In more realistic cases, what this can you can see something that looks like an exponential decay here with some finite correlation time. But this is by far simpler because you can do so many more analytical things with delta functions. So, as a theorist, we always like to make our math close in a nice tiny form. And we get a commutator actually between if you subtract these. You get something which suggests a commutator, but it's actually exact. These brackets here are not quantum averages, they are the ensemble averages, okay? This is like the reservoir average value, but even without that, one thing we can say for sure is that the commutator f of t and f dagger of t prime is delta t minus t prime. So these are even, now this is true even without reservoir averaging. Write that down for that commutator. Oops, times down. Okay. So, whoops.
What kind of noise is this?
Gaussian white noise.
Okay, so we just had to assume the Markov approximation, and then
Right.
we see that the reservoir is white noise.
Yes, that's exactly right. Very good. Yeah, and so that's related to make. If we do this calculation a little rigorously, we see different color noise. If I don't just pull everything which is frequency dependent out, saying it's slowly varying, and I can see a slightly more complicated color noise structure. And that's more relevant when you have, say, a slower relaxation time in the reservoir, or in these micromechanical systems, you can see that because the reservoir itself is a fairly small system at low temperature, so it takes a little longer. All right, let's see. We've looked at density matrix. We've looked at Heisenberg equations of motion, and now we're going to look at the last, typical thing you see in, or actually it's the first thing you usually see in quantum mechanics. Here it comes last, Monte Carlo wave function simulation. All right, so if I wanted to write down not just the density matrix, but what would a wave function, let's say I input a particular state, I know for sure my system is in this initial configuration, I don't want to know what the ensemble average over many experimental runs of my system is. Rather, I want to know what might be a typical evolution for the system to take. Right? That's what this Monte Carlo wave function method is going to do. And I'm just going to give you the outline because it's kind of a complicated programming algorithm. But we start off basically by looking at the very general form of the master equation, right? So again, the evolution of our subsystem is given by its free evolution, and now I'm not making any particular assumption about the reservoir, okay, except that it gives me, it's linear, all right? So in the density matrix, and so this is the most generic thing I can write, where C can be now any operator. It doesn't necessarily have to be a creation or annihilation operators. Specifically, you could be talking about a spin 1/2 system, and these could be sigma plus and sigma minus. C doesn't have to be Hermitian, obviously, because we've got the dagger. So these can be any set of operators, C. And this is the most generic form that is Hermitian, and it preserves the norm. It preserves the trace of the density matrix. Okay, so this part makes it Hermitian, or this part makes it Hermitian. Anyway, yeah, you need both of these to make it Hermitian, and then you need them together to cancel the trace out. So this is it. This is the most generic that you can write down. In a specific example, we'll see that the two operators are given by the creation and annihilation operator, and then these, you're going to need some dimensional weights here to give a time evolution, because rho dot has dimension 1 over time. So these operators C need to have units of 1 over root time, and that's where these root gammas come in, right? And so this is just a specific example of this very generic form that we just saw. This is what we just derived for the master equation, right? These could be very different operators, and they're from different systems. Okay, so now in order to do this we're going to work backwards from the density matrix to get a kind of equation of evolution for the wave function itself. So what I do is I split this into an effective Hamiltonian, which involves a non-real and a non-Hermitian part. There should be a dagger here in this equation. But this, of course, if I have now, if you remember from quantum, if I have a non-Hermitian Hamiltonian, I get non-unitary evolution, by which I mean the norm of the wave function isn't preserved over time. Okay, so that's what the effect of this having an imaginary piece to your Hamiltonian does. And then I separate this just into the jump operators that act now on both sides of the density matrices at once. The reason they're called jump operators is because they, in some sense, if you hit a density matrix with these operators, you discretely change it to a different state. Okay, they kick the density matrix to a different state. And if I write down what this, now substituting these back in, I write down what this form would have looked like for my harmonic oscillator that I looked at before. You get something like this. Okay, yeah, so this is, again, you can just look at what we wrote down for the harmonic oscillator, and you pick out the effective Hamiltonian and the jump operators. This is actually, there's an additional, there's an additional term here. You have A dagger rho A as well. That's okay. All right. So, as I mentioned, the effect of having a non-Hermitian Hamiltonian, you get a complex eigenstates, right? If I figure out what the eigenvalues of this Hamiltonian are, they're going to be complex, right? When you have complex frequencies, that means that you have a damped system. And it doesn't conserve the norm of rho or psi. It doesn't conserve the norm of your wave function. It doesn't conserve the trace of your density matrix. All right? So again, that's what we had for our harmonic oscillator. Now if we look at the quantum jumps, this is totally, this is a discrete kick. Again, as I mentioned, this gives you a discrete kick to your system. But it does preserve, when you put these in, now you do preserve the norm. You do preserve the trace of your density matrix. You preserve the norm of your wave function once you add the quantum jumps. So this kind of this non-Hermitian Hamiltonian removes the norm, and then you kick it the system with a quantum jump, and that puts the norm back in. Okay. So if I write down my density matrix as a sum over orthogonal wave functions with a certain probability p of being in each wave function, I can look at what is the evolution of these wave functions. Okay, so I can act on the system with these operators on both sides, and I think about the details, and then you can peel apart, basically, you can peel apart your density matrix into a particular. You can look at a particular one of these wave functions as it evolves in time. Okay, so I can kind of unpack this into a equation of motion just for a particular side out. So what I get is, first of all, a non-Hermitian evolution. Okay, I get a free or a sort of free evolution that doesn't conserve norm due to this free evolution. And then I have a quantum jump. Now, this would be not. So when I do numerical implementation, let me kind of go through the steps here. Not every, what I'll do is I'll take a small time step. Okay, so first of all, I want to integrate, I want to look at a very small time so that, say, in the example of the harmonic oscillator, I would have gamma times delta t much less than 1, so that I have a very low probability of a jump occurring at any particular time step. But low but finite. Okay, so again, I'm talking about now, we can only really do these integrals numerically at this stage when I do these Monte Carlo wave function simulations. All right, and so I say, okay, I'm going to go through, and now the probability of a jump happening, I can work out. The probability that a particular one of these jumps happens is given by delta t. So for example, if I'm talking about, that's just the third equation there, if I'm talking now about the harmonic oscillator, all right, if that's my system, remember this CI is like root gamma times A, basically. All right, and so the probability of the system jumping is something like, and this is at, I'm going to take the reservoir, let's just take n bar to 0. So I'm looking at a system at 0 temperature. I can still get a quantum jump because there's still a reservoir. The probability of that in that particular case would be something like delta t times gamma times psi d dagger a psi. Well, that makes sense. So if I'm looking at a system where it's just, say, photons in the cavity, all right, the probability of a photon escaping is equal to the decay rate times the number of photons times the small amount of time. That's basically how you compute the probability of a single photon escaping the cavity. So when I'm doing numerics, what I do is I pick a random number, and I see, okay, did the random number, was it, if I pick it between 0 and 1, is it small enough for this event to actually occur during this small time interval I'm looking at? And if so, then what I do is I hit the system prime here, because it's a new state. I hit the system with this quantum jump operator. And then, of course, I have to renormalize it, right? So that's just what that square root of delta t over delta p thing is. This is just a normalization factor that I have to put in. And if there is no jump, then I just do the free evolution, basically psi of t plus delta t. Otherwise, it's just equal to minus I over h bar times delta t times h effective. So this is like a, if random number is small enough, there's a jump. Otherwise, there's no jump during that interval. And that's a very, very thin piece of pseudocode, if you will, for how to do Monte Carlo wave function integration. So you have to code that up on the computer. There's basically no instances in which you can do these kind of Monte Carlo simulations. Exactly, but the nice thing, the reason why you want to do this is, let's say I'm looking at a system where I can't do the Lindblad, I can't do the master equation analytically, I have to numerically integrate. Well, a master equation is going to be for the density matrix, which is n by n. So for a large system, each time step I'd have to do n squared calculations, which would be very slow. If I do a Monte Carlo evolution, if I do a single wave function, that's only an n-dimensional space, right? And so I can get away with a lot less calculations per time step, and then I just average. Basically, I forget who proved that this Monte Carlo is equivalent when you average over the.
Several people, Klaus Mölmer was one of them. But I think one key point is not just so much the time, it's you run into memory problems in your computers with n squared.
Time, memory, all these things.
Yeah.
So for numeric, for computational reasons, it's useful to use this. And it does if I take the average over a large number of individual wave function runs, I reproduce the statistical predictions given by the full density matrix.
Excuse me.
Yes.
It appears to me that one could have a situation where the Monte Carlo approach would give me sort of a viscous damping, whereas the Lindblad form, the master equation, would probably never. Because if my jump operators are really observations of the variable x, then I would always suppress the bottom zero of it. I would always suppress diffusion in x, but then P could potentially diffuse.
So you're saying if you use the jump operator is x,
and I keep observing x, so the update rule for the one where you renormalize, that's almost similar to the update rule where I do something, where I measure an operator and then renormalize it. It is quite similar.
yeah.
So if I observe x on a harmonic oscillator and then use the Monte Carlo approach, by the quantum zero effect, x would not diffuse. But then I could expect P to diffuse, which is viscous damping. But then the Lindblad formalism does not have any viscous damping.
Oh, right. Then that's a different jump operator, right?
Different jump operator.
Yeah.
But then, is the claim then that the Monte Carlo approach is much more general than the Lindblad situation?
No.
Is that one?
I think the statement that Steve made is that this Monte Carlo technique works for any Lindblad form.
Right.
So now it depends on what C operators you use.
Right.
So
And the C operators that he used for his damped harmonic oscillators would not be the same C operators as you would use
Right.
So
to get the.
is anybody going to talk about quantum measurements this week?
I'm sure many people will.
Okay, so these quantum measurements are very similar to these kind of considerations about reservoir interactions, with the difference that when you're doing quantum measurements, you have a record. Kind of, it's like if you put a record of all the phonons as they come out of your system, that's what a quantum measurement basically is. Right? And so you can actually derive a stochastic master equation that is the analog of this. If you're thinking now about your jumps as being measurements, I can go back and put that in the Lindblad equation, and I can get a stochastic master equation, which is an analog. If I can do measurement with that basically, where you would see something like a localization in X through the observation of X. You can implement that, and that's just a little different than just simply damping, right? Because there's information that you gain, and so you kind of the density matrix. Remember is saying, oh, I don't have any information about my system really. I just know kind of on average what it's doing. When I put the measurements in, then you need a little bit of additional formalism. That's another term essentially that's tacked on that equation. You do the measurement, and you can implement in a similar way. You can implement both dissipation and measurements as different jump operators here in this Monte Carlo approach. So the two really will converge to be analogous. You just, when when you put that additional step of measurement in, you have a little bit of extra formalism to go through.
So the Markov assumption is essentially that you erase all this memory. Is that equivalent, or is it the same?
No, that's kind of a separate assumption, actually. Yeah, the Markovian approximation isn't necessarily that you erase the information. It's just that the correlation between kicks is because even if you don't erase, even if you're not recording it, right? The reservoir can be in a superposition of states, say, and so if you get a kick, there's some oscillation time before it'll be able to kick it again, kind of. Markovian approximation just says that's 0. So even if you're not observing the reservoir, you can still have non-Markovian dynamics. So there's many different ways to branch out from this basic formalism, adding measurements, adding non-Markovian dynamics. Some are kind of orthogonal, and some are actually it's an interesting field. All right, so the last thing I want to talk about very briefly is just about using noise as a quantum spectrum analyzer. All right, so basically, with this Hamiltonian, now we're going to go back to a spin 1/2 system. And so if you imagine that I have an atom, its interaction with the bath is a little bit different. All right? Where this f of t, I can think of this as just a random magnetic field sitting. Right? If I have an atom in a magnetic field, and then I have a little additional random component, I want to know, well, what's the evolution that's induced by this fluctuating additional component? Right? And I can figure that out in first order perturbation theory. And that's fairly, there's no double integrals, right? It's first order perturbation theory. And so what I essentially get is this, the coefficient here for the excited state, the amplitude of that excited state is given by a time integral of this noise, of this noisy magnetic field that might excite the atom. Excited state, and then I can look at the probability of occupying the excited state by squaring that. Now, I want to take the average, right? This bar here doesn't indicate that's an ensemble average over many experimental realizations. And so, if I shift the time integrals a little bit and then look at one of these going over a large time, what I get is a function, an important function called the noise spectral density. Right? And this definition comes up a lot, so it's important to know what a spectral density is. It's basically it's the Fourier component, it's the Fourier transform of the correlation function. Okay? And that's what the noise spectral density is. You look at the correlation of noise, the spectral density is just the Fourier transform of that. For white noise, it's a constant. But of course, in real world scenarios, we don't always have perfect Gaussian white noise, and so this function's useful. Then if we make some approximations about this integral, replace this with the delta function, and so forth, we can figure out the probability, the average probability of going to the excited state for small times, again, because this is first order perturbation theory, so it'll be valid for small times. The probability of exciting the atom from the ground state is just proportional to a particular component of the noise spectral density. Right? And so that's, yes?
I just had a quick question. I've heard noise spectral density single-sided and double-sided for a lot.
Yeah, that's putting a 0 here. Right?
So is there any difference physically?
Physically, what's the difference? I guess if you, right, if you're looking at a system like an optical, let's say I'm looking at like some kind of light, right, and I'm right near a resonant frequency, well, that would be a double-sided, case where you look at it double-sided, because I can go below or above the resonant frequency. Right, but if I'm looking at a mechanical system where the frequency is relatively low, I can't go much lower than that, so I kind of look at the one side. depends on the physical system, I think, when you use one over the other. Just a certain, like, if you can go to negative frequencies from your system. So, in this particular case, two-sided treatment is appropriate. And so, we can basically look at the excitation rate is the derivative of this, and it is just directly proportional to this density at the atomic frequency, basically, the resonant frequency. So the noise at the atomic frequency, or negative atomic frequency, drives the transition. That's kind of what you might expect. If I have some fluctuating field, it's only that component of the field, that the Fourier component at the resonant frequency, which drives the excitation. The other Fourier components of the noise are suppressed from driving this transition, right? And so this is an important tool. Looking at the noise coming out of your system helps understand the dynamics. For example, this way. If we look at a harmonic oscillator, well, we can do the same thing. We can put a random force, essentially. And so, if I look at what happens now when I add this force, I can look at transition rates for adding and removing phonons from the system. Okay, I go through and I do the same math as I'm doing here. I'm just plugging in a different Hamiltonian. And so I can grind through this math, and once I grind through all the math, in first order perturbation theory, I get basically the noise spectral density at opposite frequencies drives these transitions. And so I basically get a transition rate up, which is proportional to n+1, and a transition rate down, which is proportional to n. Now, in this case, right,
Backwards.
Yeah. In the first case, the bath is emitting energy. I'm exciting the transition to a higher state. And then in the latter case, the bath is absorbing the energy. The phonon is dropping, the system's dropping back down to a lower state. With picture here, where I basically look at the transitions between different populations, right? This gives me kind of a reaction picture, a rate reaction picture, and I can do detailed balance on this, right? The probability, I can look at the probability of being in each state, and it's basically just proportional to the two different, I add the probability if I'm coming from above. So this rate here and this rate here, add the probability that I'm in state n, and then adding these rates together, subtract from the probability that I'm in state n. If you look at this, okay, yeah, I've got two different ways there's two different arrows moving down. Those are these two. There's two different arrows moving up. And then there's two arrows that are coming into the system. That's those two here. And then there's two channels out of the system. That's those and those. So it looks intimidating, but it's very actually pretty straightforward. And so we can just derive a steady state, right? If I look at dp dt equals 0 for all p, what I get is a thermal equilibrium, exactly as expected. And when I look at these rates, what I can compute then is that the temperature, right? The temperature is given by this ratio once I plug this back into here. When I plug this equilibrium condition back into here, the temperature is given by this ratio of noise spectral density, and that's purely a quantum result. because classically the noise vector density would be constant. So this is a neat little way of using the quantum noise coming out of your system to tell you about its effective temperature. And thankfully, that's it.